Oh, okay. Sorry, I jumped. I started trying to solve for 0 too fast here. Okay, so there we go. So now we have our objective function in terms of a single variable x. Okay. We used our constraints to eliminate a variable. Now I want to take its derivative. I was jumping to solving for 0 already. But we need to take our derivative. That's our objective function. So we've got 2x minus 20. Oops, I shouldn't set it equal to 0 yet. So 4x minus 40, and then derivative of a constant is 0. So there's our derivative. Set that equal to 0, and now life is easy. Okay, x is 10. Now, we've got one of our positive integers that fits our constraints. It is an integer and it is positive. So we got to go back and find the other one. But we had a solution already. It was y is equal to 20 minus x. Because that came from the fact that their sum was 20. And so I just plugged in here, back plug, and I got 20, minus 10. So y is 10 as well. So there we found two positive integers whose sum is 20 and the sum of their squares is a minimum. All right, let's try another one. Let's try let's say we have the volume of a closed cylinder is 16 pi. So the volume of a closed cylinder is 16 pi. Minimize the surface area. Right. So we usually a debt giveaway, right, of what the objective function is, the maximize or minimize keywords. So we look at minimize the surface area. Okay, so our objective function, the objective is the surface area of a closed cylinder. Closed cylinder. Okay, so we have this cylinder. Lateral surface area, we just grab the circumference of a circle and drag it up by h. So I've got 2 pi r, that's the circumference of a circle, times h. 2 pi r h is the lateral surface area. 2 pi r h, grab the circumference, just the outside edge, and drag it up. But then it's closed, so it's got a top and a bottom. Area of a circle is pi r squared, but we have 2 of those. So I have to add on 2 pi r squareds. That's the top and the bottom circles. All right, so this is the surface area of a closed cylinder. That's our objective function. And we look at that and we go, okay, well, the 2 pi's, that stuff's just constant, fine. But I've got r's and h's. So I don't really know which way to go. Should I go with r or go with h? So I got to look back and say, is there anything else? Well, first of all, we can say the r has to be strictly greater than 0, right? We'd get a 0 volume. It wouldn't even be a thing if it had no radius. There's other sorts of constraints like that, but that's one that comes popping out immediately, right? But let's see, the volume is 16 pi. Well, the volume of a cylinder, how am I going to make the volume? I'm going to grab the area of a circle, so pi r squared, and drag all that area up. That'll fill the whole thing in. So it'll give me the volume. The volume is pi r squared. Grab the area, all of it, and drag it up by h. Pi r squared h. That's the volume of a cylinder. And I say, okay, well, the volume of the cylinder, whatever pi r squared h is, that has to be 16 pi. And I start looking at that and I go, well, I already got a bonus. The pi's go. They become 1 anyway. So I've got r squared h is equal to 16. That reduced my complexity already. And now I can choose. I can either choose to solve for r, but then I'm going to have a rooty thing there. I got a square root, and I have multiple instances of r up in my objective. I've only got one instance of h, and that looks like it's going to be a much simpler solution. So why don't I go h is equal to 16 over r squared. So here was my constraint, was that the volume of that cylinder was 16 pi, and I'm using that to then go back to my objective function and eliminate one of the variables h. So here I'm 2 pi r. Now h is 16 over r squared plus 2 pi r squared. Well, that's going to make life nicer. This is what, 32 pi over r plus 2 pi r squared. Okay. So this is rewritten our objective function, the surface area of our cylinder, closed cylinder. We've rewritten it now using our constraint function to eliminate the h, and now we have a function completely in terms of r. So that function, that objective function in terms of r, is what I'll take the derivative of and set it equal to 0. So I'll just move it up here for the time being. We got 32 pi over r plus 2 pi r squared. Let me just do some space here. There's our objective function. I'm going to take the derivative. Now this is 32 pi r to the, negative 1. So I'll get negative 32 pi r to the negative 2, so that's r squared, plus 4 pi r to the first power, right? Because the 2 times 2 gives me the 4, and then subtract 1. So there's my derivative of the objective function, and I want to know where is this equal to 0. So now I'm just solving for r, right? Negative 32 pi over r squared is equal to 4 pi r squared. I have 4 pi r. Negative 4 pi r. Subtract it over. Multiply negative 32 pi is negative 4 pi r cubed. Divide my stuff over. R cubed is, the negative over negative goes. I have 32 pi over 4 pi. 32 over 4 is nice. The pi's become 1. So what do we got? R cubed is equal to 8. R is plus or minus, nope, sorry, cube root of 8. So R is 2. Now, R being 2 is a positive value. It's feasible, right? We didn't come up with some negative thing. I wanted to throw one in there, but it's not an even root, right? It was an odd root, so it still came out positive. Okay, so now we found the R that will minimize this objective function. Now we can use the graph. If I recall correctly, it looks something like this, more or less, the graph of that, so that we can verify that sure enough it is actually a minimum at R equal 2 and not a maximum. But that's just a matter of graphing your objective function and just taking a look. Is it a max or a min? Okay, so we've got R equal 2, but we're not done. I guess I erased it. We'd already solved. We had that H was equal to 16 pi over, no, 16 over R squared. That came up from our constraint function, right? The pi r squared H was 16 pi. So we'd actually already solved for H in terms of R. Now that we've got R, it's just a matter of plug and chug. H is 16 over 2 squared, which is 4, so H is 4. We've got R is equal to 2, H is equal to 4. Those are the dimensions of the cylinder whose volume is 16 pi, and that will minimize the surface area. Okay, let's see. Let's try one more of that type of problem and should probably be relatively set. Let's say we have a, let's say we have 300 feet of fence. And one side of your property, is bounded by a river. Okay, so 300 feet of fence, and one side of your property is bounded by a river. Maximize the area enclosed. Okay. We should dictate what shape. It's a rectangular area. Yeah, because we could do like a semicircle or something, that of course would. But so that's going to put an additional constraint on it by saying it's a rectangular area. Okay, so I think that's enough information to be able to solve this problem. We've got this river that bounds one side of the property, and we want to build this rectangular fence such that we enclose the maximum amount of area here. Okay, so it's rectangular, so let's say this is X and X, those need to be the same, and then this is probably going to be something different, maybe not, I don't know. But I know that these have to be the same and these may or may not be different from each other. So I'll give them a different name just in case. All right, and so it says maximize this rectangular area. Well, a rectangular area is the area, is just x times y, right? Rectangular area. So that's our objective function, but again, I've got two variables in there and I don't really know which direction to go. So let's look back at our situation here. I've got this number 300 feet. Well, that's the total length of this fencing. So it looks like x plus y plus x, the total length of that fence, that's got to be equal to 300 feet. All right, so we've got 2x plus y is equal to 300. And again, we could subtract y and divide by 2 and solve for x and substitute in that way. It's perfectly legit. But this y already has a 1 out in front, so why deal with the fractions and all that business? Looks like it'll lend itself nicely to just saying 300 minus 2x. Nice. Okay, so we go back to our objective function. We take our constraint and we're going to use it to eliminate a variable. And x times 300 minus 2x. And that looks like negative 2x squared plus 300x. Now this is my area function, it's the objective function. I've substituted in and rewritten it all in terms of the one variable x. I could have done it in terms of y, but this one was slightly easier. Okay. Now, this is a good thing. I'm seeing this negative 2x squared business, and I'm going, well, that's nice. This is a parabola that opens downward. That means I'm not barking up the wrong tree trying to find a max. This thing actually does have a max, so we're good. We're on the right track. All right, so I take my objective function, negative 2x squared plus 300x. I want to take its derivative, negative 4x plus 300 set that derivative equal to 0 and solve it. So negative 4x is equal to negative 300. X is equal to 300 divided by 4. I'm going to cheat. I can do that in my head. I should be able to, but why waste the time? 75. Okay, now it didn't necessarily have to be an integer or anything like that. It could have been some root of 162 or something weird, but it is a positive integer. So talking about the length of fence, that makes sense. It's in the feasible region, I believe. And we've already got y solved for in terms of x. This is one of the advantages of these sorts of problems, is that we always have that other one solved for you. So I just have to plug in y is equal to 300 minus 2 times 75. Well, it's 150. So 300 minus 150, y is 150. And now we found the dimensions. The width, or whatever you wanted to call it, x, was 75 feet, and the length is 150 feet. That will bound 3 sides of a rectangular area. It'll sum up to 300 feet in total, and it will enclose the maximum amount of area. Nice. All right, so that should get you going on optimization problems.